Okay, now we're going to look at projectiles fired at angles. We just recently did projectiles fired horizontally, and the first thing we're going to note is pretty much all the equations we've used for horizontal projectiles apply here, but we need some extras because of the situation going on. We're first going to start with an initial velocity of a projectile fired at some angle phi. Now, as you know from class, or should know from class, that all of our equations we have are equations for vectors on the x or y axis. And the first problem we run into is the initial velocity of something fired at an angle is neither on the x or y. It's in 2D. It's in two dimensions at once. So we're going to pull out this vector and break it up into vector components using just some very basic trig. Anything fired at an angle is both pushed horizontally and vertically at the same moment. So we could figure out individually what those two pieces are that make up this resulting initial velocity at angle phi. And since Vx is the adjacent side to the reference angle, we could use cosine to form this formula to find Vx. We could use sine similarly, since this is the opposite side of my right triangle, to find the initial y velocity. Now, something that is still true even for projectiles fired at angles is whatever the x horizontal velocity is, it maintains its consistency throughout. So if we draw a diagram at where I picked just kind of 5 random points other than the peak, we can notice that the vector arrow magnitude stays constant the whole way through. And that's as long as there's no negligible, there isn't any air resistance, I should say, that's significant throughout the trip, or any drag on this object. So that's why we don't put an initial on it, because it's going to be that the whole time. But that's a different story for our y velocity, because we know anything on the y-axis is being affected by gravity. So immediately we have a Vy initial of whatever value this formula spits out for me. And on the way up, common sense tells me that y velocity at any given moment later will shrink till we reach the peak, where notice I don't have a Vy vector up here, because at that moment, just like when throwing something straight up and straight down, it has to stop vertically just for a moment at the peak. And then on the way down, it reverses its direction and gets larger and larger until we finally hit the ground and the projectile motion is over. Now, I picked a general scenario, as you could see, where a projectile was fired and came back down to the same level from which it was fired. And in a scenario like that, which they might not all be, but because of that scenario, there's a few other things we could say. But this is only true, let me stress, that if we come back down to where I started, or we're at a level from where I fired. So if I come back down to here for the whole trip, something worth noting, if we're solving any piece of the problem for the entire trip that comes back down to the same level which was fired, delta y is equal to 0. Because the displacement, I came back to where I started. And in that case, as we learned a long time ago, that means displacement is 0. Only at the position right there. So a lot of times we might want to know the time it takes to go from here to here. And if that's the case, we could say delta y equals 0. Another thing we could do at its peak, if we do know this time, let's just call it some time t, to come back down to the same level which we fired it, we could also say that at its peak, not only is Vy equal to 0, another thing we could say, the total time over 2. But be careful, remember that total time would be the time taken to get back to the level which it was fired. So at its peak, we'd have a nice symmetric parabola here, which means if we cut it in half, if it took 4 seconds to get to here, it would take 2 seconds to get to there. And one other small detail is, obviously, if we wanted how far it went from here to here, that would be known as delta x. And sometimes some problems may refer to delta x as the range of the projectile. So if you're ever asked for that, it just wants your horizontal displacement. And we will go over more complex situations in class, but that's a general strategic approach to vectors and velocities and displacements of any projectile fired at an angle.